Hi, welcome along to a little three-part video about the stars. Three parts because we're going to have how do we know about stars. I think that's probably the best bit. A bit about life cycles, a quick reminder of the life cycle of stars, which you might have done at GCSE. Technically you don't need it all, but I think without it, it doesn't make a great deal of sense. And then finally, we're going to have a look at the Hertzsprung Russel diagram, and that will mean we've now got a kind of coherent knowledge of stars. So we know a lot about stars, and you'll have heard loads of terms like white dwarf and red giant. You hear people talking about composition of stars. Well, how is it possible to know all this stuff about stars? Well, we've got our erstwhile astronomer looking at a star through a telescope, and it's just a point of light. You can't see whether it's a big thing or a small thing, which obviously kind of begs the question about why do we know some are red giants and some are dwarfs if we can't see how big they are. Well, what we can get is a spectrum. Now, this is actually a spectrum of the sun, just a reminder of something you've seen in a previous video. So we've got, we can see roughly how much energy is given out at each wavelength, and we've got these black absorption lines. Remember, those absorption lines are caused by stars, by atoms in the sun's atmosphere or the star's atmosphere. So we know what elements are in the star from the pattern of those absorption lines, just like we do from the pattern of emission lines. We can also imagine from our star kind of getting a bit of a black body radiation curve, can't we? And then we can pick out lambda max. And as soon as we know lambda max by our old friend Wien's law, we now know the temperature of that star. And because this is a red star, it's going to have a relatively long wavelength for the maximum. So if that's a relatively large number, that forces the temperature down lower. We need to make a distance measurement to the star. That might be done, say, by parallax or something like that. And of course, in our picture, we can make an assessment of how bright the star is. We can find its apparent magnitude. And we then get a feel for the absolute magnitude. And if we're looking at, a typical bright red star, then we're going to find out this indicates we've got a very, very bright star indeed. And there is an equation, we don't see it, but there must be some maths that links the power output to the star to its absolute magnitude, because this is the amount of light given at a standard distance. This is where the light's coming from. So if you've got a really big, powerful star, but you've got a low temperature, how's that possible? I mean, if your temperature goes down factor 2 and it's more than that, when you look on the temperature scale, how is it possible to get a high power output? Well, the only answer is if you have a star that is red and low in temperature with a huge power output, it must have a huge surface area. So that's how we know that there are stars called red giants, because they're the stars that have a huge surface area and therefore a huge radius. Similarly, a white dwarf will have a short max wavelength, a high temperature. If it's got a high temperature and a relatively low power output, then it must be of a low area and a low radius. Okay, we're going to do a bit about the life cycle of stars. Some of this you need to know, some of you don't, but I think if you don't do the whole thing, you don't get the picture. So all stars start as this thing called main sequence. So that means that they're in their stable burning phase, like our sun is at the moment, producing lots of energy by nuclear fusion. If we take the smaller stars, like our sun, as they come out of main sequence, they'll become a red giant. And I've always found it confusing as to why we get this red giant phase, and I'm going to explain that separately in a moment. And then as the red giant runs out of fuel, we'll get an explosion called a nova, and we'll be left with a white dwarf. A heavier star, and this M is the core mass, not the mass of the whole star, is greater than 1.4 solar masses, but less than 3. Then we go from main sequence again, we go to red giant. And then we go to a much more violent explosion called a supernova, and that becomes then a neutron star. So that's where the gravity has become so strong that it's completely overpowered any electrostatic forces, and we've rammed all the electrons into the nuclei, electron plus proton makes neutron. And you'd be looking at that thinking that doesn't conserve baryon number, so you'd expect a neutrino to be given out. And one of the reasons we're really confident that supernova explosions definitely exist in this form is that when we've seen a supernova, there's a famous one in 1987, we have actually seen the neutrinos released. And we're confident there are neutron stars. When I talked about radio telescopes and the Anthony Hewish thinking that he'd seen little green men, and Jocelyn Bell, the little trace, that was a neutron star. We know that was a very small, dense object spinning, and that was a neutron star. If you're above a core mass of 3, then again we go through a red giant or a super red giant. Again we go through a supernova, but now the force of gravity is so strong we're going to even overpower the strong nuclear force holding the neutrons apart, and we're going to form a black hole. Now the bit I'm going to tackle here is just going back to this section here to talk about why we get a red giant and why we get a nova explosion afterwards. It's probably not technically part of the specification. I just find that none of it makes sense if you don't get this bit. So here's our main sequence star. It's the core where the burning's happening. So as you know, essentially we're taking hydrogen and we're fusing it into helium. And that creates a huge amount of energy. And if you're an atom in this star, obviously not very drawn very well together, there are 2 key forces on you. Gravity, the weight, is pulling it towards the middle of the star. And a star, you know, everything's not rammed together. It's more like a gaseous type thing. So what's pushing it back out? Well, as the photons pour out of this nuclear reaction, they apply a force to this atom outwards, and so we get this radiation pressure outwards supporting the star's atoms against gravity. So what happens if you start to run out of fuel? You start not to run out of hydrogen in the core of the atom. Well, as a result of a reduced radiation pressure going outwards, our core is now going to collapse. Our core is going to move in. And as it does so, to form a smaller core, we're increasing the pressure in that core, and we're increasing the temperature because we're converting gravitational potential energy into kinetic energy. Kinetic energy is heat. So this core becomes more able to promote fusion reactions, and in a large star the helium might combine with other helium to make something like beryllium, but we're getting larger nuclear reactions going on. So ironically, the effect of the fuel starting to run out, provided you can get to a high enough temperature to promote another lot of burning, is that we now have increased radiation pressure in the outer layers of the star. So the core's got smaller. That increased radiation pressure lifts the outer layers of the star upwards. So these extra photons push out the outer layers. And because they're going up, they're converting kinetic energy into gravitational potential energy, and it's cooling, and that's why you get a red giant. Eventually, this process in the core has to stop. Eventually, we have to get to a point where either the core starts to contract and it's never hot enough to create the next layer of burning up as we go through the possible fusion events. Or, of course, in a very, very large star, once the core is predominantly iron is the most stable element. If you remember our little stability graph of binding energy per nucleon against nucleon number, iron's the peak. You can only have fusion in the direction of iron. So at that point, the nuclear reaction in the core stops. There's nothing to balance the gravity. The core collapses. There's an explosion. If it's under 1.4 solar masses, then that's a nova, and it pushes off the outer layers, leaving a white dwarf. Or if it's more than 1.4 solar masses, that explosion is violent enough to cause a supernova. We'll talk about how bright they are in a later video. Okay, last part of this video, Hertzsprung Russel diagram. Lots already really familiar here. So we've got our spectral classes along the bottom, O, B, A, F, G, K, M. Exactly the same temperature boundaries as we saw before, so that's nice. You might look at the diagram and immediately say, why is it the wrong way around? Why would anyone put the high temperature on the left and the low temperature on the right? And the simple answer is this diagram predates our sophisticated knowledge of black body radiation. And originally this was in wavelength order, and these were the long wavelengths and these are the short wavelengths. And then by Wien's law, we swapped it over, but we wanted to keep the original shape. Got absolute magnitude down the side. So our very brightest stars up here and our very dimmest stars, remember, are all compared at a distance of 10 parsecs. Really crucial that you all know that the Sun is a class G star and that it has an absolute magnitude of 5. So it's kind of quite disappointing, really. We think it's an amazing thing, our Sun, and of course it is an amazing thing, but overall that it isn't a standout performer overall in terms of stars. Remember, each step on that scale is 2.5 times brighter. So we've got this broad band. I'm just going to go, I drew it in pencil. I was so terrified that I was going to get it wrong. We always draw it as a sausage. It's not a line because it is a region of stars showing similar properties. And the history of this diagram is that somebody thought, well, as I observe stars, what I'll do is I'll plot their wavelength of their temperature against how bright they are. And we would expect to have it broadly scattered everywhere, and we didn't. And we found the vast majority of stars are on this kind of sausage called the main sequence, a term I used earlier in the video. So and we had various ideas about whether things moved along it, because what we now know is that this is the stable equilibrium hydrogen burning phase. These stars up here don't last very long. They've got so much gravity, they burn really, really fast. They're really shooting through their fuel, massive power output. Ones down here, fortunately, are going much, much more slowly. Their fuel's lasting for a much longer time. There are a couple of other regions, though, that we need to know. Up here, so what do we've got? These are lowish temperature stars with a lot of power output. So these are the red giants. And then down here, we've got low power output, but hot stars, okay? And here are the white dwarfs. And the last thing you need to know about this is that a star like the Sun, as it comes to the end of its life, it starts running hydrogen, it will become a red giant. It will burn as a red giant, and when the fuel runs out there, it will collapse back down to be a white dwarf, and we're expected to know that. We might as well just shove a few colours in while we're going. So we're going to have kind of red stars down here and up here, going through kind of orange stars here as we go to high temperatures, blue stars up here. These are our blue giants, high output, high temperature stars. Right, I'll find you some questions to do now. Thank you very much.